Hello, and welcome to EEG channel. Our topic for this video is investigating what effect, if any, would a low-frequency filter setting of 3 Hz, that is a time constant equal to 0.053 seconds, have on a 3 Hz spike and wave complex, in particular the slow wave component. We should also observe what effect, if any, such a filter change has on the spike components. Such spike and wave bursts often exhibit variance in the rhythmic frequency of the complexes. The frequency tends to begin at a faster rate and gently decreases in frequency as the burst continues. Say, for example, the burst initially fires at a rate of 3 Hz, but gradually decreases in frequency across time until the burst ends with a frequency of 2.5 Hz. We'll keep this in mind as we proceed. On this EEG page is a portion of a generalized non-motor electroclinical seizure with behavioral arrest recorded during hyperventilation procedure. Due to the pediatric patient's age and the less than 3 Hz frequency of many of the bursts, the EEG would better align with a childhood absence epilepsy as opposed to a juvenile absence epilepsy, though other generalized epilepsies cannot be entirely precluded utilizing only the EEG. A diagnosis without careful clinical consideration is not appropriate. This slow wave component was measured to be 3 Hz. The low-frequency filter is currently at the default setting of 1 Hz. Let's turn it off and look for any changes in the waveform. Notice that the amplitude of the slow wave has been accentuated, not attenuated, or said another way, increased. In addition, the curvature is smoother. Now let's zoom in and measure the amplitude of the slow wave with the low-frequency filter turned off. As a disclaimer, for this EEG page as well as the next 2 zoomed-in screenshots displaying the voltage, the high-frequency filter was decreased to 20 Hz. This was to minimize measurement discrepancies that could be provoked by the overriding faster background frequencies. Note that such a decreased high-frequency filter setting practically eliminates any frequency faster than the delta band. The amplitude was measured to be 794.14 microvolts. Using the ACNS Standardized Critical Care EEG Terminology 2021 metrics, this would be categorized as high amplitude. Now, let's look at the same EEG page with the low-frequency filter set to 1 Hz. Note how the overall contour of the curvature has been impacted. In addition, the voltage was measured to be 741.35 microvolts, which is less than the voltage when the low-frequency filter was turned off. Last in the sequence, we see the effects of when the low-frequency filter has been set to 3 Hz. Before measuring the amplitude, either manually using the scale legend or using the measurement tool, a quick visual consideration reveals a marked change from both the 1 Hz low-frequency filter setting as well as from when that same filter was turned off. The amplitude associated with the 3 Hz low-frequency filter setting was measured to be 560.42 microvolts. This is a further decrease in voltage from when the filter was turned off. Pay special attention to this next point. At a particular filter setting applicable to both the high and low frequency filters, that value indicates that a hypothetical wave with that particular frequency will be significantly attenuated by 30%. The magnitude of attenuation increases as you move away from that setting. For example, a 50 Hz high-frequency filter setting will attenuate a 50 Hz spike by 30%. That same filter setting will attenuate faster frequencies, say a 55 Hz wave, by even more. On this graphic, any frequencies within the protective triangle area are immune from significant attenuation. So, a 100 Hz gamma wave would see even more attenuation at a 50 Hz high-frequency filter setting, as compared to attenuation seen by a 50 Hz wave. Similarly, a 0.5 Hz low-frequency filter setting, that is a time constant of 0.3 seconds, will attenuate a hypothetical 0.5 Hz wave by 30%. That same filter setting will attenuate slower frequencies, say a 0.2 Hz wave, by even more. So, a 0.1 Hz slow wave would see even more attenuation at a low-frequency filter setting, as compared to attenuation seen by a 0.5 Hz wave. Now it's time for some quick math. We want to see how much the wave was attenuated from its true form when the low-frequency filter was turned off to when the filter was set to 3 Hz. One way to do this is to divide the reduced value by the unfiltered value to reveal the percentage of the wave remaining after being filtered. Since the amplitude of the slow wave with a low-frequency filter setting of 3 Hz was found to be 560.42 microvolts, and the amplitude of the slow wave with the low-frequency filter setting turned off was found to be 794.14 microvolts, dividing 560.42 by 794.14 equals 0.70569. To reveal the percentage, we simply need to multiply by 100. So, the magnitude of the unfiltered slow wave, which remains after the effect of the 3 Hz low-frequency filter setting, is 70.6%, which is very close to the expected proportion. That is, 30% of the wave's height is attenuated at the cutoff frequency, in this case 3 Hz. And that directly implies that 70% of the original unfiltered wave's height remains. We can also subtract the filtered amplitude from the original amplitude, 794.14 minus 560.42, which equals 233.72. Then we divide this value from the original unfiltered amplitude to derive the attenuation amount. 233.72 divided by 794.14 is equal to 0.2943. Multiplying by 100 gives us 29.4%, or very close to the expected significant attenuation percentage of 30. EEG Station hopes that this video has been useful for you, and if you are so inclined, feel free to subscribe to our channel, hit that like button, and turn on notifications.